So, Tom, why don't you tell everybody a little bit how you started your research?
Okay. Well, of course, as Linda mentioned, I had the honor of preparing Texas through time back a few years back, and of course, I've been a consultant in San Antonio since the '80s and worked on a variety of trends and published a lot of things in a lot of different areas. So anyhow, I was putting together the statewide, and I realized kind of that the South Texas area, particularly the Rio Grande Valley and the surrounding areas, was not had never really been treated as a whole, and this came to the fore when we had a meeting in the Geological Society of America had a section meeting that was to be in McAllen. It got moved to virtual status due to COVID, but I was chairing a session on geology of the region, South Texas Mexican region, and my job, I guess, I assigned myself the job of putting together the tectonic and petroleum system story of the area to be able to present to people what was really going on out here. And so based on that, I realized there was more to be said and continued working on it. And so that's this talk. And there also is a paper in at AAPG Bulletin on that'll cover this material. So anyway, it's been an interesting couple of years, self-funded, I should say. Nobody's paying for this other than me. Um, so it's really an integration project more than anything, and a compilation project to some degree as well.
To get started.
Oh, very good. Thank you, Linda. Great introduction. So this talk on the tectonic setting and petroleum systems really is just a second here.
I see it.
Yeah, everybody see purpose and outline? Okay. Anyway, the purpose really is to provide a basin-wide overview of the area that I'm calling Seno Mexicano. I'll get back to that. Basically, South Texas, the Burgos Basin, Northeastern New Mexico, the Cenozoic Basin, and then offshore to the deep water, to the Perdido Fold Belt and to the deep Gulf of Mexico. This is a first overview that tries to cover the entire area. So we're in two different countries and sort of three different areas, South Texas, Burgos Basin, and the offshore. The intention here is really to integrate the basin tectonics. People have done good work in each area, have some great ideas, but how does this stuff tie together? And then following on that, looking at the productive, this is a prolific gas basin, over 110 TCF of gas, and also a significant oil basin, 3.6 billion barrels or so. This number of plays with sort of distinctive features. So there's some trend analysis to look at, and then finally, how does this tie into petroleum systems? What can we say about source rock and time of migration and that kind of thing? So we're going to look at some 1D subsidence maturity modeling that helps to understand what is driving these systems and where it's productive and also where it's not productive. So there's a lot to cover, and I think if you have a question along the way, keep it noted, maybe make a chat, but some of them will get answered on subsequent slides. So first, what's this name? It really means Gulf of Mexico. It was a term, though, it was used in the 18th century to refer to the area sort of east of Monterey, up as far north as Corpus Christi area and down, what became Nuevo Santander or Tamaulipas, but also this area up to the north. So it was the only name I could find in the area that made sense for the entire basin that we're looking at. Burgos is used in Mexico. We don't, South Texas is just South Texas, So we'll look at that on the map, which is more fun. The area that we're going to be talking about is outlined in brown. So again, the Mexican onshore area, Nuevo León, Tamaulipas, is the Burgos Basin, as noted, and there's a bunch of Cenozoic fields. The South Texas is District 4, and that's basically, we'll use District 4 for all the production information. And then the offshore, which is about 2/3 Mexican, 1/3 U.S., continues down to the Perdido Fold Belt, the Baja High, this whole area offshore, of course, has fine discussion by Mike Hudek and others. Have worked on a 3D survey through here, and I'm really using their information in that deep area. We're going to be looking at a couple of key sections across here in a while. The basin as a whole is bounded on the southwest by thick crustal blocks of the Tamaulipas Arch. to the southeast by the Jurassic oceanic crust, to the northwest by the Cretaceous self margin, and to the north, it's a little bit more arbitrary, but it seems to be along this the East Breaks Fault Zone or Atascosa line that then separates it from the northern Gulf areas that many people are more familiar with. The area has 4 tectonic stages, and I'll be a little brief about some of these because we do need to get on through, but basically 4 stages. The first one is the extension of crust that formed the Gulf of Mexico basin. That happened in 2 phases, of course. The phase 1, the continental extension, and phase 2, that oceanic crust beam. We'll see this in a second. That's followed by a subsidence period in the late Mesozoic, 2 to 3 kilometers of carbonate, basinal carbonate sediments and shales and organic matter. And we also start to see 4D shales getting thicker into onshore Mexico. Then in the third stage, we have Paleogene tilting and rafting and a minor laramide folding, but the rafting being the main interesting story, and also a Lobo slide. Then the fourth stage being the Oligocene on to the present, progradation, strong progradation in the Oligocene and early Miocene with faulting and tilting, structuring. All the offshore structuring appears to be primarily this lower Miocene age, but there is a continued tilting, uplift of the west and subsidence to the east that goes on to the present day. So we'll look at these stages a little more brief, a little more detail. If you look at this on a time chart, the stage 1, the opening of the Gulf of Mexico, we have the initial deposition of basinal material. The green outlined names are organic potential source rocks for South Texas, Mexico, and some of the other central, eastern Texas names, excuse me. Stage 2, the subsidence stage, where most of the Cretaceous, carbonate section, the Tamaulipas zones, and the Eagle Ford organic shale, of course, would be in there. Then stage 3, the Paleogene, stage 4, the Neogene, and we'll be talking more about that. So looking first at stage 1, this is old information, but many people, Pindell and many others, have looked at these. Basically, we have stage 1 extension, or phase 1 extension of this, forming thin transitional crust over the whole northern Gulf of Mexico, with a bunch of northwest trending linears that take up relative extension in different areas. That's the consideration. These are identified in various places around the Gulf. They are reinforced by laramide activity in Mexico and form fairly conspicuous linears. The area of the Seno Mexicano is this box down here, primarily thin transitional crust. The true oceanic crust of phase 2, which begins probably around 160 million years, going to 140 million years, is caused by rotational opening due to Yucatan coming off. So we have this oceanic crust being deposited, formed offshore here. But we'll really be looking at the zone that's on the transitional crust. As I mentioned, this area is overlain by salt. We have known salt and salt features in South Texas. As we'll talk about in a minute, the rafting episodes extend down further south to somewhere near the Rio Grande, the national border. The area to the south in Mexico may have salt, but there are very few salt features, salt structures in the deep Mesozoic. And that may be a facies thing where we're still discussions about why that might be true. But certainly offshore, we had thick salt, which today is in the Sigsbee Canopy, and numerous diapirs in the continental slope area. So the salt was deposited across the area of variable thickness and nature. Then we had the subsidence with the Cretaceous. I won't talk more about that right now. Then we start looking at what happens in the Paleogene, the lower Cenozoic. And first, there is laramide folding. Obviously, it's very strong back towards Monterrey in the southwest. That forms a 4D basin in here. Continued folding actually extends to this dotted brown line, northeast limit of laramide folding. This folding is largely Middle Eocene in age, so it's quite late in the laramide story. It's probably the last thing that happens out here. But these are traceable up, continue on to the northwest. They form a variety of interesting features that just get over the Texas border here. So the Lopeño anticline, these kinds of things. In Mexico, they're well defined and described. They're not high relief features, so it really doesn't fundamentally change too much, but they obviously are important in understanding fields and exploration. Then to the north of that, the most significant thing will then be this Lobo gravity slide in the Paleocene, and then the Paleocene to Eocene opening of a variety of troughs, two of which are shown from earlier work, and intervening rafts. And we'll look at that next. Here we go. Just a sec. Yeah. There we go. Okay. So we're starting to look at Paleogene tilting. The Lobo gravity slide occurs in the middle Paleocene with a detachment zone on the top of the Cretaceous. There is, and it forms a multitude of small fault blocks, basically affecting sandstones, marine sands of the lower Wilcox. So there are actually sort of rafting looking things, little troughs and horse and grabens being formed, but a variety of tilted fault blocks, and it extends for tens of miles on to the southeast. This is a picture actually from the Mexican, just over in the Mexican side that's been published. The same top Cretaceous detachment occurs in Mexico and becomes the detachment for the upper Wilcox growth faulting in Mexico. In Texas, however, it's a different story, and we'll talk about that next. But in Mexico, it's the detachment and expansion and rotation is all coming on this top Cretaceous detachment. But to the north in Texas, things are more interesting and not fully understood yet. But what we have known, and is actually first Deagle et al. In 1995, paper on everything in the Gulf of Mexico, identified this Rosita trough area. What we have is the Lobo slide is just to the west of this picture, comes in here. The Cretaceous carbonates, which form pretty good reflector package, terminate here, and we get a series of major Wilcox expansion faults into a deep basin that's filled with primarily Wilcox and Queen City, Paleocene, Eocene rocks, with little or no Mesozoic rocks exposed or thought to be present at the base of the trough. Well, the Mesozoic restores or comes up again in the area to the east, which I'm calling the Mestania Raft under Mestania Grande Field and other areas, goes down into another trough area and then continues on. This is this figure from Carl Fiduk. He described these things as a raft tectonics. That is, that the Wilcox of the Mestania Raft, that Cretaceous was originally further to the west. It slid to the east on the basal salt layer and opened up a trough, which was then filled with the Wilcox. The second trough over here has more Queen City in it. He didn't go east of this because the seismic runs out and the data quality deteriorates, so you don't really get deep imaging. What's amazing or really interesting about this is the similarity of this trough raft situation to southeast Mexico, where the same kind of a thick trough with, in this case, late Oligocene to Miocene in fill, and another second trough to the north, in this case, with Miocene fill, separated by a raft of the Mesozoic sediments in the Reforma Arch area. So major production in this area, but a very similar tectonic style. Then the last thing in the Oligocene, it's a transition really to the later story. We have the low angle Vicksburg fault zone, and the only reason I put it here is it's a low angle, really a gravity slide, except here we've got more of an escalator. We're taking shelf margins and running them down this low angle slope rather than having raft tectonics. There may be some raft tectonics in it, but more we're just seeing this highly listric system on Jackson Shale that, as I say, forms the lower Oligocene, the early Oligocene story that then goes into the later tilting and deformation. As I mentioned earlier, the late Oligocene, Frio, and then the lower Miocene or early Miocene, the North Padre Delta system, are major deltaic progradations in the area, fed by uplift and volcanism to the west. We have major growth faults. These have been known for ages, but they depth to at where they may go into a decoma is not well imaged. We just don't see that image, but presumably above the Mesozoic. Offshore, the story from our good folks at the Bureau that worked on all this, we have a Bravo trough, which is filled to well over 30,000 feet with the Frio and Miocene sediments, and some later, which actually formed in their story, and it seems very reasonable, that it's the evacuation of a diapir, salt diapir, that was present in Eocene time. And that evacuation of the salt diapir formed the Sigsbee canopy, and also compression through the system resulted in the two fold belts offshore, in the Perdido fold belt on autochthonous salt, and then the Port Isabel folding on various detachments in and behind the Sigsbee canopy. There's also then continued uplift to the west that we can see onshore in the log data and even in the topographic data today. So look at this just very briefly. It's been well published by Hudek and Peel and Soto and some other papers too. Basically, what they see on a seismic line like that, it looks different on every line, of course, as things do. But basically, you come out of, in this case, Mexico, with a Mesozoic section that's actually pretty well imaged. It's further south in Mexico where the imaging improves. We come down to an area of thicker salt, the Bravo Trough, which originally would have been a kilometers thick salt diapir wall, really a salt wall would be the best determination for it, subsides, evacuates into the Sigsbee canopy, which here is kind of dismembered in several pieces. And there's folding in the trough and seaward of the trough that's very poorly imaged. Is the main issue in here, is really figuring out what the heck is going on. But down deeper, we have these folds on autochthonous salt, which are the fairly famous now Perdido fold belt with significant fields in them. As I mentioned, onshore, there's continued tilting. Now, in this case, there's a pre-upper Miocene, pre-late Miocene unconformity in South Texas that extends and can be dated by taking it out to the conformity. As you go landward, the upper Miocene here, the upper Goliad, cuts into deeper and deeper rocks. And in fact, it rests on Oligocene Catahoula and locally even on the late Eocene Jackson. So there's been significant western uplift and eastern tilting around some kind of an axis in, say, Willacy County here. We also then see this continues to the present. The Bordas Escarpment of the Goliad out here in Starr County reaches heights of up to 900 feet elevation, and that's highly unusual in the Gulf of Mexico, Gulf Coast Basin. It's being uplifted even to the present, and to the east, in Willacy County on, we have the Rio Grande Delta Plio-Pleistocene kind of system, mostly Pleistocene to recent. That forms kind of a perched wedge in the subsiding portion of this tilting environment. If we put all this in a regional section, it'll make a little bit more sense. This I did two, one in northern Mexico, and there's a variety of seismic data that controls bits of this. And so it's all, data that's been out there and been published. What we see is, of course, the green is the Jurassic and Cretaceous, mostly thickness is Cretaceous, present onshore with fairly little bit of structuring, a few faults and so on. Most of the detachment on the top of the Cretaceous. The Eocene detachment is just very conventional looking, I guess, on that, followed by then the Oligocene-Vicksburg-Frio, extension of the Vicksburg and Frio fault zones in here. Continuing to the offshore environment, where we go into kind of the Hudek land here, and we have the Bravo trough, again, Oligocene-Miocene, not thought to have any Eocene in it, really lying on what would have been a salt diapir out here. And if you remember back to the map, I have to, and the efficiency of not putting a map back in this part of the section, but this diapir, this trough that was a diapir, is highly continuous from the southern end of the basin all the way to the northeastern end of the basin. And it loses its distinctiveness as we cross the East Break Zone and get into the central Gulf area. But it's a very long and very major feature that has evacuated in the Oligocene Lower Miocene to form the Sigsbee salt canopy complex out here, and also then separate this area of Cretaceous and Eocene rock out in here. Now, there's no evidence in the structuring that's been seen offshore of any compressional activity prior to the late Oligocene, early Miocene. And everything out here seems to more or less have happened together, the folding and the salt canopy and the evacuation. It's just one complex of activity. So if we look at northern, we go north. So basically we have Bravo extension up dip, mostly in the Oligocene, Miocene, and then we have the compression down dip in the fold belts. If we look at South Texas, we have that system also, but we also have an earlier system. So what we see here going from up dip to down dip, here's the Cretaceous again in green. We see this raft, the first one being the Rosita trough with Wilcox, the second one here, the Premont area with Queen City. And I'm proposing there may be a third one. It's not imaged. We don't know this, but one that might contain a better thickness and possibly character of Eocene source rock. We'll talk about that in the petroleum system story. That's speculative. We'll see. However, what happens to all this extension here has to go into compression somewhere. It did not go into the today's slope environment because that doesn't show any compression until the late Oligocene. Where did it go? Well, it pretty much has to have gone into the coastal zone where we don't image it. We can't see this stuff, but there has to be a fold belt or a thrust belt or whatever it is of deformed Mesozoic strata sitting out here that takes up the extension on these 2 or 3 troughs that we have. And what's interesting about that is that line of deformed Mesozoic would be a linear lode that could well have generated the Eocene diapir, which is now the trough just to the south. So the concept or the conjecture here is that we've got this Paleocene rafting that's pushing a Paleocene-Eocene fold belt of Mesozoic strata over the thicker salt, pushing it up into a linear salt wall that extends perhaps 150, 200 miles long. And that then in the Oligocene-Miocene is deflated under progradation of those units, forming the canopy and all the fold belt activity that we see also. So we have 2 extension compression complexes, the Rosita of Paleocene to maybe Eocene age. Then we have the Bravo extension and compression couple of late Oligocene to Miocene age, all in one section here. So that's my conjecture of what's happening. Again, we can't image any of this material down here in the deep section. That would be so wonderful to have. So that's the tectonic integration. That is the status of that. We want to look now at the gas production and the petroleum system. So I won't detail, you could get into boring detail with this, but remember this is a major gas province. It's produced just from major fields over 50 BCF, 81 TCF estimated. Gas production for Texas is reconstructed since we don't keep cumulative totals in that zone. And we're not including casing head here. It's just gas. 16% from the fields in Mexico, and that's a pretty good number for a breakover in gas. 16% there and 84 from the US side. Total production is over 110 TCF of gas occurring in 7 trends. We'll look at those in a minute. That's actually larger than the Eagle Ford estimate. So for whatever that's worth, it's also a significant oil area, not super prolific, but there's several good trends and important oil zones in the area. And we're not totaling up condensate or natural gas liquids, which have been important in this area as well. So if we look at where these trends are, and we'll just touch on these things, but it's important to look at them. The oldest here is the Lobo slide area, which is nicely outlined by the fields. Really from the edge of Laramide thrusting here north through Webb County, 12 TCF of gas, number of major. This map shows all major fields and labels all giant fields. So that's the way to look at it. And so we have a field here with 2 TCF of gas. Now that's a complex of many, many fault blocks. So that's the Lobo slide, a little bit in Mexico, mostly on the US side. The Wilcox fault zone is expansion faults in Mexico. There are expansion faults in Texas, but the ones up here are going into the Rosita Trough. The ones down in Mexico are going on the upper Cretaceous. This zone has cummed 14 TCF of gas. Both of the Wilcox plays are essentially dry gas. That's significant. There's a barren zone to the east, more so in the U.S. than in Mexico, and then there is production, but minor production. And then the big giants really are the Vicksburg Fault Zone, which extends as a discrete unit really from just into Mexico all the way north through South Texas, with these major fields that are almost continuous 40, 50 mile long fields. We have different names for parts of them, hundreds and thousands of reservoirs in them, in the Frio and upper Vicksburg particularly, and then lower Vicksburg to the east along the Vicksburg Fault Zone in this light purple color. That cumes 27 TCF of gas, 861 million barrels of oil. The native juice coming into that section is a gas condensate. So it has significant condensate at depth. As it comes up into shallower environments, it disproportionates and we get oil rims on gas caps, which is the traditional mode along the Vicksburg Fault Zone. As we go down dip, there are continued major and giant fields in the Frio, 24 TCF and 884 million barrels, includes Reynosa in Mexico and Víboras, and a number of fields up towards Corpus Christi. The number and size of fields decreases seaward. There's only a few of them when you get to the east part of this. And when you get to the Miocene, there's almost there are no giant fields and not very many major fields out in the Miocene shelf trends. So we have a barren zone, we have this productive and extremely productive zones, then a barren zone, and then the significant production of the Wilcox. We also have oil trends, the shallow Jackson section in South Texas, shallow depths, heavy oil, no gas. And then a whole section of the area around Nueces County, Corpus Christi, is more oil rich, has actual oil fields in it, not just oil rims. And so that's marked off. That's more a transition to what we see in the Central Gulf to the northeast. So the very pronounced striping pattern in here, and a real curious question of where did this stuff come from and why does it behave the way it does? Why is the Miocene so poor, and why is the Claiborne perhaps not so poor in this area? I won't give you all the answers because I don't know all the answers, but we'll do what we can. If you look at the production on pie diagrams, again, Texas versus Mexico versus the federal lands offshore, and you can see that Texas is about 80% of the production in gas. 2/3 of production is from the Frio and Vicksburg, half of that from Frio Fault Zone, half of it from Vicksburg Fault Zone, about 1/3 from the Wilcox, which is divided between the Lobo and the Wilcox Fault Zone. If we look at oil, then again, there's about 2/3 from the Vicksburg Fault Zone and the Nueces oil area. A lot of this is oil rims in the Vicksburg. It's not the major production, but it's very significant. We have the Duval oil, somewhat less than 1/3, and the Perdido area, a substantial and growing wedge, of course, from the deep water fields. If we look at these on the cross section, South Texas cross section, we can see what they look like. We've got the Lobo and Wilcox sitting down in here obviously in the Wilcox, sitting at the edge of the Rosita Trough, particularly the landward edge, and the Lobo slide that sits behind it. And again, these are dry gas zones. We have the shallow Jackson Yewa oil, which is a separate thing. And then we have this major constellation of fields in the Frio Vicksburg Fault Zone, and then the Frio Fault Zones over in here. The deepest major fields sit right along the toe of the Vicksburg Fault Zone and the first major Frio. So this would be Víboras, Monte Cristo, and other interesting fields. And Reynosa actually might go to that deep, but there's some deep fields in there. As we go seaward, those go upwards in the Frio and become less frequent. And then we have this large barren zone at the coast and offshore where we have thick Oligocene and Miocene. And then finally, way off to the right, there's the Perdido fold belt fields in Eocene rocks primarily with we'll talk about sources in a second. So that's very pronounced geographic segregation, but these are very extensive along strike. All right, let's just close with hydrocarbon systems. There are 3 major zones that we can talk about in the Gulf. The major the cluster of source rocks in the late Jurassic, both carbonate hosted and clay shale hosted. The Pimienta in Mexico, La Caja, Bossier, give it your names, Smackover related things. Probably the Bossier is the most systematic regional, major Gulf-wide marine source in all the basins that we know about. Again, that is over mature at present in all the deep Gulf of Mexico and all the deep basin here. In the Cretaceous overlying, of course, it's the Eagle Ford is the biggest zone in the mid-Cretaceous. And that is, of course, an outcrop, and it's obviously a significant play right around the fringes of the basin. But it is, at least in the gas window there, and it's over mature again in most of the Seno Mexicano in the deeper part of the basin. Then the third source is going to be your Cenozoic sources. And in particular, this is the Paleocene, the Midway, and the Eocene, particularly Claiborne, which is a known source rock in Louisiana for oil. Down here, we never see it. Nobody's ever, got a core of it or anything. But we do, there seem to be source rocks in there. One suspects that most all of that is Eocene in age because of basically the changing in oceanography and climates as we go into the Oligocene. We have much less organic matter being preserved in these slope environments. So we'll be talking about that, and that becomes significant. How do we look at these in terms of each of the plays? I'll just show you a few 1D subsidence and maturity models. The first two here from the Wilcox, the left-hand one being the Lobo Pescadito area, and the right-hand one from Culebra in Mexico. That gets us out of difficulties of thinking about the Rosita trough and how that works. But you can do the same thing up there. What we see is a steady subsidence this is compaction corrected and all that. We see a steady subsidence in the Mesozoic that steepens in the early Cenozoic, comes to a maximum depth of burial probably in the late Oligocene. And then there's Neogene uplift in the western area. It affects the Wilcox plays and the Mexican area more than it does to the east. So it's a distinctive feature of these plains that we have this sort of uplift later on. The source rocks are in purple for Jurassic down near the base of the column. The green is the mid-Cretaceous Eagle Ford zone. And then the brown will be the reservoirs that we're talking about. The Lobo deposited at this point and then has this subsidence curve. I'm not showing the sources that might exist in the Cenozoic because they're quite diffuse, so we don't know where they are really. But you can see where they are, either the Paleocene here with the Midway, that'd be just below these rocks, or the up here in the middle and upper Eocene particularly, maybe distal Wilcox somewhere, but not in this area. That might have source potential in different areas. Probably less so here because we have more terrestrial coarse clastics and so on in some of these zones. But if we look at the maturities windows coming across this through time, we see that the Jurassic was reaching maturity and going through its gas window really in the upper Cretaceous. So it's much older than the reservoirs, and the structures, which are right after, immediately follow the reservoir deposition. Then those things are well over mature by then. The Eagle Ford, however, has a broader range, and obviously there's some uncertainty in detail here, but one suspects that dry gas generated, particularly from the Eagle Ford, could have been migrating up through the system along some kind of trend, like that, and be charging these zones. The Cenozoic zones are both unfavorable in facies and also largely non-mature, although the Midway could contribute at a later date. If you look at the Culebra, similar story. Again, the upper Jurassic peak, maybe 9 million years older than the reservoirs, but Eagle Ford within 2 million years. So very plausible to use Eagle Ford sourcing in these areas that could be consistent, particularly with a dry gas that we see. Now, it should be pointed out the reservoirs in the Wilcox are all today deep into the gas zone. So any oil that was present could well be cracking or half cracked in those zones, and you would really need to look at bitumen and to refine that story. If we look at the Vicksburg and Frio trends, we use one from the left is from the Vicksburg fault zone, Kelsey Field. On the right is a Frio field, more or less along the line of section. And what you see in here, what Kelsey is particularly telling, is that all of the Mesozoic reservoirs are passing through the gas window basically in the Wilcox, Paleocene, Eocene time, and we've probably lost that hydrocarbon. We don't know as we go seaward. It is suspected that the Eagle Ford becomes less rich, and we're looking at the Jurassic zone, but it doesn't make much difference here. There's probably not that much thickness out here. As we go when we look at these windows, we see them crossing the Jackson-Claiborne, however, and which would be a potential source interval in this area, pretty close to the deposition of the reservoir. So the Eocene peak would be near the reservoir age, and vertical migration out of this zone would be very, very easy to imagine. As we go to Raymondville, it's a similar story. It's a little harder to do, mostly because there's so little deposition before the Oligocene loading that we actually are closer to the Mesozoic sources being mature, or at least in the gas window in that area. So it's a little harder to say for sure that there isn't a contribution, but we really don't know anything about the Mesozoic sources because they're down in that imaging gap, and we're also getting towards the area that's probably got compressional deformation. So who knows on that, basically. But again, the Eocene sources work quite well for that. And also notice that both of these, when you get out in these zones, the reservoirs today are immature, right? So all of this is coming from depth, and that's characteristic of these more seaward plays. So what does all this look like? This is the last slide, and it has a lot on it. First place, we can sort of generally define an oil and gas window. This is cognate to the cartoon I had in Texas Through Time that people seem to use. So I decided we needed to do one for South Texas and the Seno Mexicano. So looking at that, we have a tilted oil and gas window through the entire area. This is largely due to the Cenozoic repetitive history of tilting that continues to the present. So rocks are actually in the oil window at outcrop as you come back into western Webb County, right? The gas window is very shallow. As we go eastward, the gas window deepens, and many of these rocks are in the oil window or immature. As we go offshore, then the Perdido in its deep water environment also then is in the oil window. The source rocks in purple and green and the Mesozoic down here are today over mature through the onshore basin and to the Bravo Trough, if present. However, as we showed in past time, the Eagle Ford particularly is likely to be the source for the dry gas in the Lobo and Wilcox zones here, which are also in the gas window, so they are subject to cracking as well. The Vicksburg and Frio are gas condensate originally, and they seem to be focusing on this set of Frio faults at the toe of the Vicksburg fault zone, if you want to think of it that way. That the Vicksburg could be, well, it can be sourced vertically or it can be sourced laterally. We don't know the details of that, but there's certainly a significant source that's sitting down about in here that was producing gas condensate in Oligocene time. And how much and where it located, it could be in some of these troughs, so the Premont is a bit up dip from where you'd want it. That's why I suspect there might be another trough with thickened slope sediment that's sitting down underneath this area. I think it's called it the Weberus Trough somewhere. That's just a name. But some kind of trough down here. It's never been imaged that I know of. But as we go seaward, we lose that because we lose Eocene sources. The Eocene's ponded in these troughs and then up against this deformed Mesozoic zone. And it's really not present. Then in the Bravo Trough, of course, we again Oligocene to as far down as anybody can determine it. So this area is barren. We have no Eocene, and well, we have is Oligocene. Some of that's basinal, but we're not seeing decent sourcing, and that's the general story there. Of course, as we go to deep water, then we have contemporary oil zone conditions in the Jurassic and Cretaceous. So it's easy to source those things. We understand that pretty well, thanks to work of a variety of authors on that. So in conclusion, then, we have from the hydrocarbon story, what we've got is basically a Wilcox and Lobo zone of dry gas, tiny bit of condensate occasionally, pretty much dry gas. It's in the gas window. It was in that area, the Eagle Ford was in the gas window at the appropriate time. There might be a little assistance from like Midway shales and the Rosita Trough, or et cetera, but that's probably second order. Vicksburg, Frio and Vicksburg fault zone trends, gas condensate with some oil, particularly to the north. They are has to be sourced from the from the Cenozoic, from the Eocene, in the that are sort of mixed terrestrial marine zones. The Duval oil is an anomalous case, and it may represent a shallower clayborne oil source somewhere. It's not really well determined where that might be, but somewhere in the Duval to Premont Trough area, perhaps. And then as you go further south, when you don't have the Eocene presence in the subsurface, we have little production, and that would be the outer zone, outer coastal, and the Bravo Trough area. So with that, that's my story for today, and I'll be happy to take questions. I see there are a few in the chat.
Hey, thank you, Tom. Wow, what a great synthesis, so comprehensive. So when you do regional studies like this, you can't help but see things that maybe need a little more exploration effort. And so I was wondering if you could possibly share some of your thoughts on general areas. And as you know, Dick Bishop and I are fascinated with giant fields. Where would you, if you were looking for giant fields, where would you go? Any tips or hints for the audience, perhaps?
Well, think what I can share there. The onshore, of course, it's pretty, has been heavily explored over the years. I'm not sure I see, a large amount of remaining potential. There's some interesting things going on in the Clayborne, particularly in Mexico, where you have significant Queen City fields and significant Jackson fields. And those are zones that really don't produce on the U.S. side. It would be really interesting to maybe go into some of the area along in the southern part of South Texas and say, well, there could be similar things over there, and really look at the geology in there. Whether that's going to be giant, I don't know, but it could be significant. Then, of course, the main sourcing, I'm kind of thinking of the biggest zones, the Frio and Wilcox Frio and Vicksburg are down along the sort of Monte Cristo Vivaris trend. And how deep do the sands go in there? There's been great production down to 15, 17,000 feet, but that means it's at the bottom of the world or not. What's of interest in my looking at the map, I'll just throw it out because I'm not going to work on it. As you check, there's sort of a consistent trend from Monte Cristo to Vivaris, and then you kind of lose it. Something reorganizes at that point as you go towards Corpus Christi, and you get a different, sort of an offset zone that might go under Saxet and Baldwin and all that area. How that really works is interesting. There's certainly down to 10. There are Wilcox, deep Vicksburg tests down into the Frio fault zone area, and they've been interesting. They haven't been productive yet. There's some interesting structural complexities involved in that. There seem to be kind of stacking of structures along some of those zones that it's very peculiar. I've just seen it on a seismic line or two, where you start saying, well, there's something down deeper that's doing something, and it's not multiple, it's something. So that would be worth looking at. And then offshore, the biggest thing besides continuing Perdido trend stuff, which is, again, mostly in Mexico, but we have some, is also the whole Port Isabel area is probably in the oil window. And if you have reservoirs, get the Eocene up into some of those zones, they could be really nice. The problem that seems to exist in there is just imaging. It's pretty chaotic, even on the 3D data. What the heck is really going on in there? And that may lead to small reservoirs that wouldn't be commercial, but might not too, so that would be something to look at. Okay, maybe that's enough for right now. Got a message here. Oh, do you want to read it? Says, do you think the Lobo and Vicksburg slide complexes are ultimately rooted in deeper Jurassic salt withdrawal? A field size would suggest that they are. It's a good comment, and that the rooting of these gravity slide type zones has never really been understood. I'm not sure I do, other than they seem to root in a deeper into the next deeper fault zone. So that the relationship would be really interesting to look at, particularly if you have good seismic data and wells, that could be quite interesting. I think basically you're seeing the tilting business, the uplift to the west, subsidence to the east. That seems to begin back in the Paleocene. The Lobo, of course, is an instantaneous slide. The Vicksburg probably took a little bit longer, but Vicksburg doesn't take a lot of millions of years. And it's not a long-lived episode. The compression that slide would suggest must have occurred may have been the opening of the Rosita, and this get kind of taken up into the Rosita. But the nature of that could get very complex, and it would be really interesting to know more about that. So yeah, I think to me the two may be related, at least particularly for the Lobo. The Vicksburg, I think, goes into the Frio fault zone, and then that takes up on some kind of décollement in probably the base of the Oligocene or some kind of lower Cenozoic zone that's not well understood. I don't know, but to me it does look like it's focused along that the join basically. That would be interesting. Okay, next.
I've
Yeah.
worked the Frio Vicksburg early in my career, and it's not a very porous rock. So
Right.
it's also very heavy in volcanic rock fragments, whereas the Wilcox is
Right.
in volcanic rock fragments. So
Right.
I guess is the Frio coming from eroding a volcanic area up in the Denver area?
Yeah, that's good point. That actually was the next thing on the list here, so that's marked well. The Frio Vicksburg typically is tight, and really, yeah. Of course, the Catahoula is exposed in the Frio area, has boulders of volcanic rock in it, and it tied back particularly to the Trans-Pecos area and the alkaline volcanism trend and the Trans-Pecos. And the Frio in general, as the Catahoula, the Oligocene, the whole Western Gulf, is full of volcanic rock fragments and ash deposits, and those are going to lead themselves to generating pseudomatrix and occluding your porosity, unless you have early migration, and you can maybe forestall some of that, but it's less likely. The Wilcox, as you mentioned, is pre-volcanic in that sense. So what you're seeing, debris that's coming, from the Rocky Mountains being developed. The Rockies or Sierra Madre are getting into that. I've not seen the full petrography on that. I know it's out there to look at, how much is carbonate and how much is, say, granitic and that kind of thing. But it definitely is not volcanic in nature. This is not a time of great volcanism. And so it's going to tend to preserve porosity. Again, with the assistance of early migration of hydrocarbons and all that too, and secondary porosity. So, yeah, that's always been the problem, and really starts in the Iowa too. Is typically lower porosity rock as you get into South Texas than what you see up to the Northeast. From Janet, let's see. That's just a thank you. Enjoyed seeing the Vicksburg in better and newer seismic data, and it's when I worked on things back in the Pleistocene, whenever it was, you draw a section through South Texas, and you could draw in the fault zones in the Frio and Vicksburg and all that, and then there's this big white space underneath. So this is the first diagram I know that fills in the white space. It may not be right, probably isn't in detail. I'd really love to get more of that, but that's kind of the principle of it. The relationship of rafts and the Bravo Trough want to be clarified. The rafting that we know about, which is the Rosita area, and Carl's put together on that, that would have to be, it's filled with Wilcox, which is, the fill is lower Eocene, early Eocene age. The rafting itself could be equivalent to the Lobo slide as a mid-Paleocene, could be late Paleocene. It may be sequential. Wouldn't probably be instantaneous, but it would seem to be lower Eocene in age, whereas the offshore, the Bravo Trough is formed in the Oligocene. The late Oligocene is when you form the trough. But according to Mike's story on that was a prior diapir, so it was a salt wall that deflated. It's of interest that back when Deagle wrote in 1995, his proposal for the Rosita Trough was that it was a salt wall that deflated. So salt walls and rafts can give you similar appearances. The difference really, to me, one thing is it's kind of hard to see both where the salt would have gone to, that we don't have a salt canopy or even a deflated salt canopy related to the Rosita, which you certainly do as you go to the Bravo. Now, the Bravo, you have the Sigsbee canopy story on some lines immediately offsetting. It's really beautiful. Go back and look at Mike's paper on that. Some of them are more like what I showed, where there's kind of broken up and goes along quite a bit further. So that's the main difference there. And the Bravo trough is later. So there's really two. If you think of all gravity tectonics being basically extension in the head wall and compression at the foot, right? So it's like a landslide, the old landslide model, and it's a good thing to keep in mind. So we have the extensional area of the rafts. We have the compressional area related to those rafts, and that can't really be seaward of the Bravo trough trend. So that's why I propose that it's there under the coastal zone. And then the Bravo extension compression takes place from the upper Oligocene, late Oligocene into the Miocene, and then peters off as the loading and progradation dies off in the middle Miocene. So that they're different things. And but I do, as I said, I think the compressional zone of the rafts may be forming the diapir that then becomes the Bravo trough in the later stage. So it'd be a several stage operation. Let's see. Somebody asks, are you tempted to tie the tectonics of the Rio Grande Rift and into the tectonics of the Great Basin? We'll leave it. And are there striking similarities in tectonostratigraphic sequences? Short answer is probably no. But really, the Rio Grande Rift per se tends to kind of die into Mexico, and it's really hard to define a definite zone. But there certainly is extension of that extension is primarily Miocene in age, and again, there's a thermal doming and sort of mantle source to what's going on, and the extension of plate tectonic source for that extension. That would be earlier. It does generate a large amount of uplift. And one thing I hadn't really got a chance to mention in that is that we have some reasonable fission track evidence from some years back that there's up to 5 to 7 kilometers of erosion in the Monterey area in Mexico. And we see good evidence of erosion all the way up through Coahuila. We see, exposed plutons, cyanitic plutons, that were originally at several kilometers depth when they were emplaced, that are early Cenozoic in age. These, the continued uplift, which really goes all the way up into the hill country of Texas and a more modified version. But the real peak of that is down to the southwest. That is the biggest area. That appears to be middle, maybe Oligocene, and then really the uplift, the initial of that uplift is really what's generating these big deltas into South Texas and Mexico. So the Rio Grande story is probably mostly later than that, but there may be some relationship why that doming occurs and what's driving that ultimately. I think that's a good story for another talk. Let's see, and the last one I see here is that is the last one. As you said, somebody says, what are the unsolved issues in the area? It's like, yes, everything. This is the first time to kind of try to put the parts together. The people that have worked, things that have been set up in Mexico, which often is better. There's some better data availability in Mexico than there is in South Texas. It's remarkably little written about South Texas. I mean, the only paper on the Lobo that talks about it was 1986, and it's like 5 pages long, and written by a good friend of mine. But we know more. We should know more, but it's just very little has been published. Even in the Vicksburg, there's some, but it's sparse, and some field things, of course. But anyway, it's not well put together. So this is a first try at putting it together, basically. So certainly there's going to be a lot more issues. The big thing is we need really want seismic that can image to 6 to 8 seconds in the coastal zone. And so far, that nothing I've seen or heard of has done that. The ion lines don't, in my memory of it, I don't have them in hand, don't image in that area any reliability. And that's where this putative Paleocene, Eocene fold belt would be, and that whole imaging area in there. That's difficult. Maybe in the offshore shelf, as we get to the northeast part, that some of the lines might be better. nature of the salt contact into Mexico is kind of interesting also. And I'm sure there's more. Everything needs better substantiation. What can I say? Christine says, how do you explain the close proximity of the Eocene fold and thrust belt compression, Mexican compression, and the Gulf of Mexico growth faults? Thinking about what that is. The Eocene, I guess you're thinking about that diagram with the map with the Mexican, the Laramide folding coming in from the southwest. In general, this phase of the Laramide, of course, huge, goes from Alaska to Cuba, if you want to make it that way. We're looking at the Mexican phase called an Hidalgoan or whatever. And this zone, we really see, of course, there's a high intensity deformation, fold and thrust belt in the Monterey area, particularly because that's partly detached on salt back in there. In the front, we have these broad uplifts along the thicker salt pieces of the Tamaulipas Arch, and then these low intensity folds off to the northeast. How those, I've never seen, and the Mexican literature talks about that in terms of particularly, of course, the Wilcox and Queen City fields. Those trend off to the southeast and must underlie that deformation must underlie some of the coastal belt. But that's never really, it's below the depths that people have looked at. And so I don't think we really understand that. The growth faults, as you come down, as you go southward into Mexico, they tend to die off and consolidate. That's really because you're coming out of the deltaic center. You're going to the deltaic margin. Ultimately everything vanishes as you go to the south and southeast. So there's kind of a complex relation there, which I don't have any details on, but just from what's out there available is approximately how that works. Did you observe any strike slip or wrench tectonics in the area? Ha ha ha. No, I haven't observed them yet. One suspects, or I would suspect, that these northwest trending linears, and they are significant, come into this area. The Lababia Zapata transform is the one that I like the best. So it basically comes from Big Bend area, south of the Serranía de Burro, and then it comes briefly right around the bend in Starr County, and be the Zapata County, Starr County area, and to the southeast. And that seems to be very significant. Presumably it would have Jurassic strike slip, but that's below anything we've drilled, and might be seen on some seismic. I have not seen that seismic to know. In the Mesozoic, that becomes a hinge line zone, probably holds maybe that edge of Laramide folding, maybe related to it. One thing we do see on the border has interesting features. And in fact, of course, it would be really interesting to shoot a 3D on both sides of the border for 5 or 10 miles, but a little hard to put together. But you have a variety of features. We have this fold belt coming in, low intensity fold belt, maybe Lockhart Field, maybe Lopeño, and a couple of those, and then into Mexico. As you go seaward, that also then becomes the Vicksburg at Sam Fordyce. The Vicksburg fault zone curls around and parallels the river and forms San Fordyce Field, and then kind of drains on south towards Reynosa. How that really works is not known. There's got to be some strike slip, a Blake slip in that area, you would think, to make that work. And there's a similar one actually in the lower Frio. The next Frio fault zone does something similar to that as well. So there's some funny step backs in there that may be controlled by a deeper basement, or at least a Laramide feature or something. But nature of that control would be impossible to say right now. Anything else? That's all I see right now. So, right. Agreed. All righty. Got one last message here. Oh, just thanks a lot. Okay, thank you much. Well, I don't know about the living encyclopedia. Anyway, a lot of great stories, and I'll come tell some more someday. How about that? All righty. Take care, guys. Farewell.